Section 1.9 is the matrix of a linear transformation. So this was alluded to in section 1.8. And what we're going to find here is that any linear transformation T will have a unique standard matrix A that represents its transformation. Now, we need a couple definitions before we can get into that actual fact. But first things first, we've got this idea of standard basis vectors. So if we're in the space R2, so the set of all two-dimensional vectors or vectors with two entries, then we define the standard basis vector E1 as 1, 0, and the standard basis vector E2 as 0, 1. So in an n-dimensional vector space, Rn, E sub n, the nth standard basis vector, is the basis vector whose all entries are 0 except for the nth entry. So here the second entry for E2 is 1, everything else is zeros. The first entry for E1 is 1 and everything else is 0. E1 in three-dimensional space is 1, 0, 0. E2 in three-dimensional space is 0, 1, 0. And there's a third standard basis vector in three-dimensional space, E3, which is 0, 0, 1. So that kind of gives us a brief introduction to standard basis vectors. The next thing we can do with standard basis vectors is put them together. We take all the standard basis vectors for a space. So in R2, there are 2 standard basis vectors. In R3, there are 3, and so on for any n-dimensional real space. But if we take the standard basis vectors as columns in a matrix, then we'll form this matrix given here as I2. I2 stands for the identity matrix in R2. Typically, we'll probably drop the subscript in future uses of this, where the dimension of the size of the identity matrix is just known from the context. But to be more specific about things and exact, the subscript may show up from time to time. So this is called the identity matrix, and I think we saw back in the previous section why this would be the identity matrix. We had a set of 3 or 4 transformations for which we observed what the transformation did to the unit square. And we found that this transformation specifically didn't change the unit square whatsoever. It didn't cause any shearing. It didn't reflect or change the points in that unit square whatsoever. So if you look back at 1.8, you'll find that example. Thus, it's the identity. If we apply it to points in space, we get back those same points. Or if we apply it to vectors in a real space, we get back the same vector we multiply by this matrix. So let's find a matrix representation of one of these transformations. That's our first goal. So this problem tells us that T is a linear transformation from R2 to R3, such that T of the first standard basis vector, this is an R2 of course, so it looks like T of 1, 0, is equal to the three-dimensional vector 4, 0, negative 1, okay? Similarly, T of E2, which again looks like T of 0, 1, because this is a vector in R2, gets mapped to 1, negative 2, negative 3 in R3. So we're taking vectors in two-dimensional space, 2D vectors, and mapping them to 3D vectors through this transformation. Now we're told that this transformation is linear. So with that being the case, we'll use a property of linearity in order to figure out what the formula for this matrix is. And then from that formula, I'll be able to take us one step further and show that we actually have a matrix that's behind all of this. So in order to find a formula for T of x, where x is some vector in R2, that's our goal, is what we want to find here. So, well, the first thing we should write is this. Well, T of x is equal to anything in R2 has components x1, x2. So if we can make this vector look like these two vectors somehow, or a combination of them, we can use the linearity of T in order to come up with a formula for T for any general vector T of x, as we have highlighted right here. So the trick to doing this is to realize that we can split the vector x1, x2 as the vector x1, 0 plus 0, x2. So the extra step in here we don't see is this. We can decompose this vector in the following fashion. Absolutely fine, right? It's true by vector addition. And the next thing we could do is factor x1 out of the first vector and x2 out of the second vector, and we'd be left with an expression that looks like this. So this is exactly what we've done after writing down t of x. We wrote down its equivalent form, equivalent expression right here. So the last thing we can do, since t is linear now, is we can split up this sum. It's t of each of these vectors. And we can also factor out a multiple, the multiples against each of these vectors. So we end up with x1 t of 1, 0, and x2 t of 0, 1. This is a rule for linear transformation that we saw in section 1.8, one of the last results we just saw in that section. So you can refer back to that if you need to refresh your memory there. So when this is written, the whole point of getting here is now we've got t of 1, 0 written down relative to our general application of t to a vector, or to application of t to a general vector. But we know what t of 1, 0 is. That comes from above. It's 4, 0, negative 1. So now we can fill that in the next line. So t of x is equal to x1 times this vector plus x2 times, well, t of 0, 1 gave us this vector. And we've got this expression. Combining each of these, we get a vector in R3. This is written in vector form, we see. When we move to the right, where we actually have a matrix multiplication going on. But this is our first entry is 4x1 plus x2. Second entry is negative 2x2. And our third entry is negative x1 minus 3x2. Now note, we could write this sideways too. We could lay this out and express it as 4x1 plus x2, comma, so on, negative 2x2, and finish it out with the third one. And we could write t's formula this way as well if we wanted to. But maybe more usefully, we can look at this and realize there's actually a matrix multiplication going on behind all of this. If we look down this column for the x1s, we realize we have 4, 0, negative 1. And we have a coefficient column of 1, negative 2, negative 3 for x2. And we can write that as the coefficients times the x vector. So we have this coefficient matrix A times x1 and x2 to get exactly this output vector. So not only have we found the formula that we might have been asked for, and this is probably the answer in my lab or in other forms when they ask for the formula of the transformation, but I've taken it a step further because it was obvious to do so and form this as a matrix as well, right? So our standard matrix here is this for the transformation T. Now you'll notice there's a shortcut. Once we've done this once and we know how T acts on the identity or the standard basis vectors E1 and E2, or however many standard basis vectors there might be in our domain space, if we know how T acts on all of our standard basis vectors, then all we have to do is take the columns at each one of those outputs, put them in order, and form a matrix A. So that's your shortcut to do this in the future. But now that we've done it as is, we see that yeah, it's plausible. We have more or less a sort of a justification, but not a proof for the theorem that's down below. So if T is a transformation from Rn to Rm, then there's a unique matrix A such that T of x equals AX. Now, in order to prove all this more generally, what we'd have to do is say that T acts on n of these vectors, and just take this one step further into abstractness to make sure it's true for T acting on n vectors with m rows, and we could easily generalize this argument to prove this theorem here. Notice the second part of the formula or this theorem here gives me what I was suggesting before, right? That we can just take the columns of T's image on the standard basis vectors and just form the matrix from that. It's exactly what this line right here is saying. So if A is the n by n matrix whose jth column is the vector T of the jth standard basis vector, then we can form A in this fashion right here. And that's exactly what we did before. We used T of E1 and T of E2 in our example because there were only two standard basis vectors for R2. So there we are. Now, let's take this just a bit further and talk about finding the standard matrix in a more general case. Now, perhaps we're given the formula for T of X. So T of X is equal to -3 times the vector X. This is odd. It doesn't look like we have some kind of set of transformations here, but we do. It's just sort of implicit by -3 times that vector, that scalar product of -3 and the vector X. So, and to see that, we write this down and say, okay, T of X is -3x for some X in R2, right? For any X in R2, actually. Well, in X in R2 looks like this. It has components X1, X2. So let's make, if we're looking for the matrix A, we need T of the standard basis vectors. We need to represent, we need to see what T does to each of these standard basis vectors. So in order to do that, let's decompose X1 and X2 like we did before as this sum here. Then we'll factor X1 and X2 out of that. We have this situation. And then we can distribute the -3 to each of these vectors and actually multiply it into the vectors at both of the ones here, the only places are going to hold the -3. So we have X1 -3, 0, and then X2 0, -3. These two things are added together. Again, if we view this as a matrix transformation, we see, or if we treat T in terms of its linearity, the fact that it'll move through these constants and act on T of 1, 0 to give us -3, 0 with an X1 multiple in front. I think that's probably harder to see than just looking at it and realizing that this is simply the matrix -3, 0, 0, -3 times X1, X2. Or the other way to think about it is, well, we can form A simply, and this is the shortcut again, A is equal to T of E1 and T of E2 is the second column. And what does T do to E1? Well, it multiplies 1, 0 by -3, so we get -3, 0. It multiplies E2 by -3. E2 is 0, 1, so it gets 0, -3. So that's the shortcut that we could have used here, but this is just a demonstration to take us further into the details once again. Now, what I advise the reader to do is to check that T of V times any vector, make up a vector, maybe 1, 2, and make sure that this transformation, -3 times the vector 1, 2, gives us the same thing that this matrix A times that vector 1, 2 gives us. And that's just a spot check, right? It's not a full check, but you should see that it is in fact equal. Okay, so another transformation, and this is probably one of the last times we'll consider a transformation geometrically. And of course, we've only done that for objects in the plane, at least in terms of graphing it and really kind of digging into what it might look like. But this is a transformation of rotation. So T, we're going to let be a transformation from R2 to R2, which rotates each point, and we'll think of a point as the terminal side of a vector in R2. It will be just the same as a point. And it rotates such a point or a vector by an angle of phi in the counterclockwise direction, which is the positive direction if we remember from trigonometry. Okay, so phi in the positive counterclockwise direction. So in order to come up with a transformation that does this, let's draw a vector v. So here's an arbitrary vector v. It has components v1 and v2 in the space R2. And if L is the length of this vector v, and by the way, if we're going to rotate v so that it becomes a vector u, if we're only rotating the vector, then the length of the vector doesn't change. So notice that we're using L over here for u as well. So L is the length or the magnitude of v and u. Now, remember from polar coordinates or converting from rectangular coordinates to polar coordinates, that if we have the length of this vector and we have the radius it forms with the positive horizontal axis, or what used to be the positive x-axis, then, and that angle is theta, then we can express V1 as L cosine theta and V2 as L sine of theta, forming that right triangle right here. So if that's the case, then we can do the same thing for this vector u that's been rotated from V by an angle of phi. It has length L as well. Its distance from, or its angle from the positive x-axis is phi plus theta. So that's what we see in place here, or theta plus phi. And that gets us a representation of u as well in terms of L and theta and phi. Now, the next thing we'll do is we'll take each of these expressions and we'll split them apart using the sum identities for cosine and sine respectively. So over here we see the sum identity applied to cosine theta plus phi with this multiple of L, and we get this expression here. But when we look at this expression on the side, this is our sum identity for cosine theta plus phi, we see L cosine theta. Well, that's V1. We also see L sine theta, and that's V2. So we'll write that in terms of V1 and V2. After all, T is going to map the vector V with components V1, V2 to the vector U with components U1, U2. So really, we add one extra line here, we'll see what's going on. U1 is equal to this expression. This is a function of V1 and V2. In fact, it's a linear function of it, right? We just take V1 and V2, multiply each of those functions by cosine phi and sine phi respectively, or negative sine phi respectively. U2, the second component of U, is equal to this. And after we do a similar simplification using the sum identity for sine, we have V2 and V1 here respectively, and we're able to write this down. Now, what does T do to the vector V then? V1, V2? Well, it outputs U1, which is this, and U2 in the second component, which is this. And if we pause for a look at this momentarily, we realize that, well, V1 and V2 are the variables here. Remember that phi might look like a variable, but it's some fixed angle that we're deciding to rotate this, or some decided upon parameter that we'll decide to rotate the vector V through. So these are the coefficients of V1 here, and these are the coefficients of V2. So if we write that coefficient matrix down, we have this matrix A, our standard matrix for the transformation T. This is a really common matrix that you'll see in mathematical applications. Things like fluid dynamics will use these rotation matrices for vectors or vector functions even. So it's nice to know where it comes from, how it can be derived, rather than just using it all the time without exactly being sure where it comes from. So nice example to have seen there. So let's dig into some properties of linear transformations. So you might remember this from previous classes. Maybe we've heard of onto before. I think we've definitely heard of one-to-one as it pertains to functions. But we'll say that a mapping T is onto, so, or a transformation T from Rn to Rm is onto Rm. And it's going to be like what it sounds like. So this statement is Rn into Rm, and the mapping may or may not be onto, but if it is onto, then each B in Rm is the image of at least one X in Rn. Okay, so let's say this a little bit more clearly down below. For each B in Rm, we can find an X in the domain. So for each B in the codomain, we can find an X in the domain such that T of X is equal to B. In other words, if we pick a B over in the domain, the codomain side, then we can find an X that T will map to that B. And that's the idea of something, of a transformation or a mapping being onto its codomain. It essentially covers every point in the codomain. Okay, and that's opposed to being one-to-one. These are two completely different ideas, even though they're always sort of taught or thought of together. One-to-one is slightly different. It says that a mapping, we have that a mapping or transformation from Rn to Rm is said to be 1-to-1 if each B in Rm is the image of at most one X in Rn. So at most is key, at most one X in Rn. So there could be no X in Rn, 0 X's in Rn satisfies at most one X in Rn. So what this is saying is that anytime we do map to B in the codomain Rm, then there's only one X value that does that. There's only one vector in Rn that does that. So another way, a better characterization of this, which could be proven, but it's pretty straightforward to do, is that T is 1-to-1 if and only if, so this is an equivalence, T of X equals T of Y implies that X equals Y. So this part of this statement is not usually there, so I'm only highlighting the typical way that we'll write this. But to clarify what this is saying is that if B is equal to T of X, or maybe put it the other way, if T of X equals B and T of Y is equal to B, then of course these two things are equal to each other. If T is 1-to-1, then X and Y have to be the same thing. If not, then we'd have more than one item mapping to B. Okay, so this is our useful characterization of 1-to-1 right here, this implication right here. If we pick up some X and some Y and claim that they're equal to each other, T of X is equal to T of Y, then it must be the case that they're, we call X and Y the pre-image, that the pre-images are equal to each other. If the images are equal, then the pre-images must be equal. That's another way to say that as well. So that's our 1-to-1 idea. So let's see how this connects to a linear transformation. So we're given the standard matrix of a linear transformation T, which maps R4 to R3. So R4 to R3. And we can see that by the fact that we have a 3-by-4 matrix, 3 rows by 4 columns. So we have to multiply against a vector in R4, and we'll get an output of a vector in R3. Now the question is does T map R4 onto R3? And another question is T a 1-to-1 mapping? Okay, well, let's pause real quick. I want to point something out. This matrix A is just the coefficient matrix for a transformation. It's not an augmented matrix, so don't jump too far ahead. If you looked at this as an augmented matrix, you might say, aha, that's something I'm going to keep in mind. This is inconsistent. Well, it's not. This column is not a right-hand side column. It's still a coefficient column. So it's okay that it has a leading entry in it here. If we were talking about this as an augmented matrix, there'd be one more column to the side. And in fact, I will do that in the work that ensues below. So remember that when we're talking about a 1-to-1 mapping or an onto mapping, we're really asking a question about AX equals B, right? So in other words, A being the transformation of, or the matrix of the transformation T, we're asking in the case of onto is for every B in Rm, can we find an X that solves this system? In other words, for every B in Rm, is there a solution to this equation? If there is, then that means we can find an X that solves this equation every time. Well, that tells us that we can find an X such that A of X equals B. So we can map X to B through T or through its matrix A. So that really boils down to a question of, well, writing this down, the augmented matrix with X1, 2, 3, and 4 here, and then putting this into echelon form. And I'm going to put it into echelon form with leading ones, right? We already have an echelon form here, so that's fine. And we could probably make the same deductions here, but I think just visually it looks a little nicer if we have ones in our leading rows. So we divided this row by 3, that includes B2, and we divided this row by 7, and that includes B3. Notice that, and this will always be the case, we can't mess it up over here, right? B1 through B3, the one thing we might worry about is dividing by 0. Well, we're dividing by 3 and 7. There's nothing we would divide by that could cause any trouble on the right-hand side. So really, we're mostly focused on what happens over here. So, do we have a solution to this system, right? Once we get into row echelon form, we can determine whether or not this is a consistent or inconsistent system. In other words, one with at least one solution or one with no solutions. Well, if we check, we usually go towards the first or the bottommost non-zero row, or the bottommost non-zero. There aren't any total rows of total zeros, so we just go to the bottom row in this case. What we're looking for is a zero, or is an inconsistent line in here somewhere, right? All zeros, and then that infamous asterisk, right? Something that's potentially non-zero. We don't have that, right? We have a leading code. We have a leading entry in each of our, for each of our rows that is not in the rightmost column. So we have a consistent system. Now, if it has a unique solution or infinitely many solutions, it doesn't matter. We're consistent, which means that for any b value that we have, any b vector we have over here, there's always going to be a solution x such that ax equals b. In other words, we can always map an x onto any given b. So t is in fact onto. Okay, that's all rephrased down here of what I just said. Now, is t 1-to-1? So the other thing we want to consider is the fact that, sure, we had leading entries in all the right places in every row here, and that's good, but we do have one free variable column. Now remember, if we have a free variable column, this is x3, by the way, x3 is free. That means it can be infinitely many different values. That means there are infinitely many solutions. Well, that means for any b, I can choose x3 to be whatever I want, and it can be different values. If x3 is different values, then my vector x, or my vectors x that map to b, will be different vectors. So there's more than one vector, and those vectors aren't equal to each other, which map to a single b. So t is not 1-to-1, right? That's maybe the quickest way to dispatch that. For any b, ax equals b has infinitely many solutions because this variable here is free. And if that's the case, well, t is not 1-to-1, right? So not only are there more than one solution for any b to this equation here, but there are infinitely many solutions for any b. So that's very much not 1-to-1. It's maybe a way to think about it. So maybe we can get some slightly better tools for determining whether or not a major transformation is 1-to-1 or onto. And that's what the next couple theorems are about. So the first theorem is more a setup for the main theorem down below. Okay, and the main theorem is what we use to determine whether or not a transformation is 1-to-1 or onto in the future. It could be the most convenient thing to use. So let's first look at an intermediate theorem we need. If we have t, a linear transformation from Rn to Rm, then t is 1-to-1 if and only if the equation tx equals 0 has only the trivial solution. So let's recall. I'm going to sketch a proof of this. It doesn't have all the rigors of a standard proof. It'll give us a rough idea of why this is true. So remember that t being 1-to-1 is summarized by this implication here, this conditional statement. That's the key thing to keep in mind. Now we're proving an if and only if statement, or we're talking about the proof of an if and only if statement. So this is a biconditional. This means that t is 1-to-1 implies that this equation has only the trivial solution, and this equation having only the trivial solution implies that t is 1-to-1. So both of those implications are given respectively by these arrows. Going the forward direction, t being 1-to-1 implies that t of x equals 0 is only the trivial solution, and then vice versa. So to prove a biconditional, oftentimes we'll break it up and we'll do one implication and then the other. Keep in mind that each of these statements, t is 1-to-1, well, that's the same as this implication. So that's one side of our equivalence, which is also part of it, which is a biconditional or sort of a bi implication. And this is also a conditional statement as well. if t of x equals 0, then x equals 0. That's what that means for that to have only the trivial solution. So it's a little confusing as to how all the logic gets sussed out here. But for the forward direction, we assume that t is 1 to 1, and then we assume that t of u is some vector such that t of u equals 0. Okay, then if we can show that u is the 0 vector, or necessarily the trivial solution, then we've established that the forward direction of this implication. So use a vector such that t of u equals 0, then t of u equals t of 0, if we were to write that down, which will be true because t of 0 we know equals the 0 vector, right? And t of u we've assumed is equal to the 0 vector. So this follows from that. Well, since t is 1 to 1, this implication kicks in and tells us that u must be equal to 0. And so what we've got now is that if t of u is a solution to this, then u must be 0. That tells us that t of x equals 0 only has the trivial solution. So we've confirmed that that's the case thanks to this 1-to-1 property of t. Now, if we go the other direction and assume that this t of x equals 0 has only the trivial solution, then we need to show that t is 1 to 1. So we assume this: if t of x has only the trivial solution, then t of u equals t of v is equivalent to the equation where we subtract t of v from both sides, so minus t of v on both sides, and then use linearity of t to write t of u minus v. And the right-hand side, after subtracting that t of v, is 0 anyway. So remember, the intermediate step here is that t of u minus t of v equals 0. So here's our intermediate steps for this equivalence. Well, t of u minus v equals 0, this statement is very useful to us. We've assumed that this has only the trivial solution, which means that the only way this is ever true is if this argument is 0. Well, that means that this argument here, u minus v, must be 0. So as we've written here, which tells us that u must be equal to v. So at the beginning, we had t of u equals t of v, and that implies that u is equal to v. That's exactly the statement for 1 to 1. So thus t is 1 to 1. So now we've got a really nice fact. T is a 1 to 1 transformation if and only if it has trivial solution for the homogeneous equation. Or if it has only the trivial homogeneous solution, might be a short way to say it. Remember, this is a homogeneous equation. So we'll use that to prove the theorem below, and I'll at least sketch the proof here, even though I think we've talked reasonably through some of this in the previous example. But if we have t, a transformation from Rn to Rm, we assume that it's linear. We let A be its standard matrix. Well, then we have two facts, or two equivalences. T maps Rn onto Rm. In other words, T is onto if and only if the columns of A span Rm. Now, I won't do all the details of this proof. This one's going to be truly more of a sketch than anything, but we'll tend to that in just a moment. B tells us that T is 1 to 1 if and only if, so this is equivalent. T being 1 to 1 is equivalent to the columns of A being linearly independent. Okay, now the key insight for each of these equivalent statements, A and B, are given below. So Tx equals B is really the concern, right? We want to know whether or not for every B in Rm, we can find an X such that T of X is equal to B. Well, that amounts to A of X equals B, or A times X equals B, which is really just a linear combination. Remember, matrix products with vectors are linear combinations of the matrix columns, and whether or not that's equal to B. So this translates us from T being onto, which means that for every B, we can find an X such that T of X equals B. Well, that's the same as saying that there's a linear combination of the columns of A that's equal to B. So for any B in Rn or Rm, we can find a linear combination of the columns of A that's equal to B. Well, that's the same thing as the span of A being equal to Rm, or in other words, Rm, or A spanning Rm, because we can generate any vector in Rm through a linear combination of the columns of A. Okay, so that handles onto more or less, right? If T is onto, if and only if we can generate any vector in Rm as a linear combination of the columns of A. Now, and this is kind of a nice similarity, we'll see down below that T being 1-to-1 has to do with the homogeneous equation. So we need a chain of equivalences first, though. So we recall that A of x equals 0 having only the trivial solution is equivalent to the columns of A being linearly independent. That's from section 1.7. If you go back and look, we have a theorem there that tells us that. So AX equals 0, the homogeneous equation having only trivial solution tells us that A has linearly independent columns. Okay, now further, AX equals 0 if and only if, well, this is our vector version of that multiplication. So what we're interested in here is whether or not we have a non-unique solution to this linear combination. So what we can connect to above is the fact that, well, okay, A being linearly independent is equivalent to AX equals 0 having only the trivial solution. But we know that from above, AX equals 0 is TX equals 0. And if it has only the trivial solution, then T is 1-to-1. Well, then we pop out immediately with it, right? So we know that T is 1-to-1 if and only if its matrix A has, its homogeneous equation AX equals 0 has only the trivial solution. And if that's the case, then that's equivalent to the columns of A being linearly independent. Now, it is interesting to note that both of these onto and 1-to-1 deal with a linear combination of the columns of A. One concerns whether or not we can hit every B, and the other one's concerned with whether or not we have non-trivial solution to the homogeneous equation. So that might be the element that we use in a lot of cases to determine whether or not a given matrix or given transformation is onto or 1-to-1 by looking at its standard matrix A. So one more example to wrap all of this up and put these things to use and maybe clarify what we're going to deal with is the following. So we let T be a transformation on vectors in R2. So T takes x1, x2, and it maps it to R3. Look, we have 3 entries in this vector. So we go from R2 to R3 in this fashion. We're asked to show that T is 1-to-1. And then we're also asked whether or not T is onto R3. So let's stand this vector up vertically to make it look a little bit more like what we're used to. T of x1, x2 is equal to, and we made this a vertical vector as well. And we've got this expression. Now we can go through all the work we've done before of, well, what does T do to the identity vectors, right? We could just remember our shortcut. A is equal to T of E1, T of E2. We use all the standard basis vectors for our domain. Our domain is R2, so we only have 2 standard basis vectors. We could plug in 1, 0, and 0, 1 to each of these lines. But what we'll get ultimately is this same matrix down here for A, right? Again, I've taken those extra steps just to show how these decompositions work. You don't have to use these steps. Typically, you can just use the theorem that we had at the beginning of this section to get through this. So the key question now, or the key thing to do to answer these questions, is to convert this matrix A, our standard matrix for T, into reduced echelon form. I like reduced echelon form because we can really get into the details of what's going on. So if we look at this reduced echelon form, we realize that we have two basic variables. And we also note that every column has a basic variable, both of the columns really. So with both columns having a basic variable, it leaves room for no free variables. A has no free variables, so it only has unique solutions. It only has the trivial solution for AX equals 0 is the most important part of that. And when we know that, we use the theorem on the previous page to deduce that T is 1 to 1. Right? We're using this top theorem here. And that handles 1 to 1. That was nice and quick because that theorem is so helpful. Now, the reduced form of A, reduced echelon form of A, does not have a leading 1 in row 3, right? We look down here and realize, okay, row 1's got a leading 1, row 2's got a leading 1, so far so good. And then we get to here and realize row 3, one of our rows does not have a leading entry or a pivot position, however we might want to call that. If you go back to the equivalence theorem in section 1.4, then you realize that a matrix, the columns of a matrix A span R3 or RM, it's an image space if there is a leading 1 or a basic leading 1 or leading entry in every row of its echelon form or reduced echelon form. So since we don't have a leading 1 in the third row, it fails to have a leading 1 in every row. So it fails to span this space. And if it doesn't span this space, remember over here, in order for it to be onto, it must span the space. If it doesn't span the space, it can't be onto. So T is not onto. Okay, so maybe it's a little complicated jumping back and forth between the theorems, but what we're really looking for is to get any transformation standard matrix into reduced echelon form, and then look for free variables. If you find a free variable, it's not onto. We're looking for leading entries in every row. If you don't have a leading entry in every row, it's not onto. Oops, I might have said something incorrectly. If you don't have a leading entry in every row, it's not onto because it doesn't span the image space. If you don't have any free variables, then you're 1 to 1. So that's maybe the summary of that. Okay, so take a little bit of practice, but it's not a terribly difficult concept. And again, the heart of it is to convert a matrix to echelon or reduced echelon form and make deductions from there. That's the theme of most of the sections in chapter 1.